Hi, I'm Jan and welcome to our session here at Works With by Labs on giving your hardware brains and ears with embedded machine learning. This session is going to be really amazing because rather than just me standing here talking to you, we're going to do an actual workshop and we're going to really build your very first embedded machine learning model. And something that is that small that can even run on a small little dev board like the Thunderboard Sense 2. So this dev board can actually start responding to things that happen in the physical world, like whenever you say, hello world. So really cool. We'll start with a short introduction. I'll tell you a little bit about what embedded machine learning is, what it's good for, and then we'll dive straight into the workshop part of this session. So I'm the co-founder and CTO of a company called Edge Impulse. And Edge Impulse was built by engineers for engineers that want to add machine learning as a new tool in their toolbox. So what does that actually mean? Well, before I founded Edge Impulse together with Zach, my co-founder, we both were at ARM. And we saw firsthand the amazing number of new devices that came out with ARM technology every year. I think ARM is up to about 30 billion with a B, number of devices that are partnership or MCU ship every year, an astonishing amount. But we also saw that these devices do very little typically. You'll have a device that sends some data to the cloud or over a sub-gigahertz network somewhere, but it's often very low resolution sensor data. And the world is much bigger around. The world is much bigger, and think about all the things that you could potentially sense. And we figured embedded machine learning is the way to actually make sense of these large sensor streams, which we're going to be demonstrating here in the session. And we figured, okay, let's start thinking about what it would mean for an embedded developer to utilize machine learning in their product. That is Edge Impulse. We're an end-to-end platform where you can start collecting data, training a model, verifying that the model works, to solve kind of any problem where you know that there's sensor data on one end and there's a conclusion at the other end where it's really hard to write the control loop yourself. We're an open platform. We've partnered with Silicon Labs to bring support for the Thunderboard Sense 2 to market. So if you have one of those dev boards laying around, it's fully supported by Edge Impulse. You can get started in a couple of minutes. We have example projects on anything from detecting weird vibrations to listening to your voice, to detecting other audible events or scene recognition, and even higher value cases like stuff like image detection or object tracking. There's already over 35,000 projects created. It's an astonishing amount. And if you want to be one of those people, just head to edgeimpulse.com and sign up for free. So why out of these billions of devices are so many of them kind of do very little? Like, what is the reason behind that? Well, it's sort of because it's easy to build relatively easy applications. So let's say that you want to get the temperature outside, a very basic kind of IoT 101 demonstration. It's very easy. You go to DigiKey, you buy a thermistor or analog thermometer, and that's it. You connect it to your dev board. You then do a little bit of calculations to convert the voltage to whatever the temperature is, and then you can send it to the cloud or somewhere. And there's a whole bunch of these type of easy applications. So temperature is naturally one, push buttons are another one, very simple, just a single input. Hall effect sensors to detect when a magnetic field changes, for example, to see when cars are parked. All really cool, but limited in what they can sense about the real world because we're limited to the sensors we can just buy off the shelf from our distributors. There's a whole world all around us where much more interesting things are happening, that you can't just buy a sensor for. For example, if I want to detect whether an elephant is nearby, I can't go to DigiKey and buy is there an elephant nearby sensor and connect it to my dev board. But as a human, it's relatively easy to detect if I hear an elephant. I can just listen for the trumpet sound. So how do we transform something that we as humans can very easily kind of hear or sense and translate that something that a machine could do? And that's where kind of I think the really interesting part is, because once you are able to do that, then all these infinite sounds and images and motions and everything around us becomes accessible on the computer or on your device. And it also allows us to do much higher resolution sensor processing. So think even if you have an accelerometer on board of your device right now, chance is that you sample some data, maybe every 10 minutes, you look at the peak motion or the average motion, and that's it. The rest of all the data that that sensor could potentially collect is being thrown away. So we're utilizing sensors that might have a sampling frequency of 1,000 hertz to then kind of downsample that to maybe one reading every 10 minutes you send over. And that's not because we don't want that data, but it's because, well, it's probably cost prohibitive to send all of the data to the cloud to analyze, so it needs to be local, and that means you probably have bandwidth and power constraints. We're here at a conference by Labs. They do a lot of really low power parts. If you have, your sensor attached to a battery powered device, there's just a kind of an upper limit of stuff that you can do, especially when networking gets involved. So this is where machine learning can kind of help. It's not that we don't know that there's a correlation between an elephant trumpeting or the waveform that generates on a microphone and the elephant trumpeting. It's just that it's really, really hard to write a control loop in your application that detects that. Because it's a lot of data, an audio file would be 16,000 values, 2-byte values every second, which is a lot of data. And there's a lot of potential combinations. So writing the rules in the same way as you'd normally write, your normal application to detect an elephant trumpeting or whether you see something on a camera, really, really hard. So a traditional approach of I have an input, and then I, as a programmer, write rules, and then based on those rules, there's an outcome, that kind of falls apart on these types of sensor interfaces. So I'd like to see machine learning not as a magic box where you throw some stuff in and something comes out, but rather as a different way of writing that application. So rather than say, hey, I have an input and I have rules, and then outcome comes from that, I say, well, I have input, a waveform of an elephant trumpeting, for example, and an outcome, this was an elephant. Go find those rules for me. So you switch the stuff around. And the cool part is that a computer is really good at this stuff. The great part is that once you've found those rules, there's nothing different than if you would have written those rules yourself. It's just mathematics, and our computers, our dev boards, even measly Cortex M4s running at 40 megahertz, like on the Thunderboard Sense 2, are really good at executing that stuff. So embedded machine learning kind of gives you the opportunity for anything where you have messy and high resolution sensor data to start to make sense of it. And that's where embedded machine learning shines. And thanks to a whole bunch of advancements in technology and the stuff that we're building, but also the stuff that lots of other companies in the ecosystem are building, it's possible to make these rules as small as possible to actually make them run on an embedded system, which we're going to be doing in the workshop after this. So if you look at kind of applications, naturally you're recognizing sounds. That can be humans, or it can be just audible events. Glass breaking is a very standard example. Biosignal analysis. So one of our largest customers is a wearable manufacturer, and they use embedded machine learning to detect if a person is healthy, if there's something weird going on, what type of activity they're doing. You can think about it in the sense of industrial or maintenance, detecting abnormal vibration patterns, for example. And if you think about even higher compute use cases, this is maybe not Cortex M4, but on a Cortex M7 you can do a lot of this, even stuff like classifying images. So you can really give your sensors eyes, which is amazing for obvious reasons. There is so much visual information in this world, so much stuff that we can easily see as humans, but a machine can't. And if you add some eyes to your device, all of a sudden, you expose that. So to build your first ML model, we're going to be doing this right after this. It's incredibly easy. First of all, you need to gather some data. So we built this full data collection client for the Thunderboard Sense 2 to collect data from all the sensors. That is fully supported by Edge Impulse. But you can take any other dev board, attach our data forwarder to it, and just send some data from that. Then we want to extract some features. So even though we say machine learning, I'd like to think that the machine learning is great, but if there's a different way of getting intelligence in that signal, do that first. So we're a strong believer still in digital signal processing as kind of a first frontier. Clean up your data, get some interesting features from that. And only then we start learning from the data. So that could be a classification problem. What am I seeing? It could be a regression one, like what is the value of this thing? Like how full is something? How much water is flowing through a pipe? Or is what I'm seeing, is that normal? Yes or no? And finally, deploy it back to device. As said, it doesn't matter how you find these rules. After the rules are found, you can just treat it as code, and that's what we do. So if you deploy your model from a Jimpulse, we'll just spit out a C++ library, fully hardware accelerated, that runs really nicely on all of your Scilab silicon. So does that sound exciting? Then stay on, because now we're going to be switching to the demo.